one of the difficulties of Scikit Learn and machine learning is to know which model to use, because how to use a model is in general quite simple. I just need to fit it and then I can predict. This comes a bit with experience and a bit with knowing simple rules, such as to experiment with the gradient boosting regressors. But also, a lot of this is by comparing models empirically on the data. And I will discuss a bit how we can compare those models. So I can create a k-nearest neighbor regressor. I can fit it to data, and I can measure its confusion matrix. Okay. I can do the same thing with other models. And what I will need to do is that I will need to measure their performance on test set to make sure that I have a good measure of performance. For this, I can use the validation set, so I can use a train test split to leave out data, and then I can get a correct measure of performance for my two models. And I can compare the two models. And then I can select the model that works best. So I can select the model that gives the smallest error on the validation set. For instance, here I am comparing three kinds of models: the Gaussian naive Bayes, the k-nearest neighbor classifier, and the linear SVC. And I will measure their error on the test set. So each time I will fit the train set and measure their error on the test set. And then I can choose the one that predicts best. So here it's the k-nearest neighbor classifier. I can also compare different parameters of the model. So here I'm looking at a variety of parameters, the number of nearest neighbors, or the loss in the linear SVA. And this is how I can empirically choose my best model. Here, in the first example, I've done this using one single test set. However, I may want to do this many times, splitting many times, because I will get a better measure of my prediction performance. And you need to keep in mind that those measures are noisy measures. They're imperfect. And if I want to choose the best model, I need to work to get the best measure possible. For this, I can use cross-validation. The idea of cross-validation is to repeatedly split the data in train and test many, many times. And Scikit Learn has tools to implement this cross-validation. There is, for instance, cross-val's core, which is found in Scikit-Learn.model selection. And the way it works is that I give it a model X, Y, and optionally the number of splits that it needs to do, or how it needs to do those splits. So here I'm asking it to do 5 splits, and each time it will split out data, train on the train set, test on the test set. And now we get 5 measures of error, and we can compare those measures of error across the different models to pick the best model. So we can use different splitting strategies, and this is done by passing objects to the CV arguments. So for instance, we can do a shuffle split. The shuffle split will shuffle the data and then split it. The nice thing with the shuffle split is that I can increase the number of splits, keeping the same fraction of the data in the test set. So I can compute many splits and average across those many splits. There are many different cross-validation strategies, and they are detailed in Scikit Learn, in the Scikit Learn documentation. Now, now that I have this technique to measure the performance of a model, I can use it to tune its parameters. So for instance, the nearest neighbor classifier has the parameter k, and I may want to tune the parameter to take the best possible model. This is known as hyperparameter optimization. Another example is that of ridge regression or lasso regression, which are both linear models that have a parameter, which is a regularization parameter. And I need to set this parameter empirically. So I can compare those two models, the ridge and the lasso. The ridge and the lasso are two linear models, but they have a different regularization. The regularization of the ridge forces the model to keep small coefficients. The regularization of the lasso makes the coefficient sparse, which means it gives a small number of non-zero coefficients. So I can compare the ridge and the lasso. So for this, I will use cross-val score on ridge and lasso. And I'm computing the mean of cross-val score, and I get two different answers. The ridge, I get 0.4, and the lasso, I get 0.35. So in general, in Scikit Learn, bigger is better. So given this experiment, I will conclude that the ridge is a better model for my data. However, both ridge and lasso have a hyperparameter known as alpha, which tunes the amount of bias that we put in the model. And we need to put just the right amount of bias. If we put too much bias, we will have a model that is too simple and it won't predict well. If we put not enough bias, we will have a model that is too noisy. And here, I haven't done this. So what I can do is that I can vary this parameter value, alpha, and I can use cross-val score each time to compute the prediction accuracy for the different values of alpha. So I've done that here, and as I vary alpha, you can see that the models have an optimal, and then they predict less well. So I have two different optimals for lasso and for ridge. So based on this figure, which model should I prefer? The lasso or the ridge? Well, based on this figure, it seems that the lasso predicts better. So I would conclude that I should prefer lasso. However, can we trust those results? Here, I have used the data to select the best alpha parameter. Given that I've used the data to select the best parameter, I need another test set to evaluate my model, because I can never evaluate a model using data that I have already seen. And so for this, we need a way of selecting alpha only on the trained set. never looking at the test set. And the way we will do this is using grid search CV, which is an object that will take a model and take a list of parameters to vary, well, a dictionary of parameters to vary. It will perform internal cross-validation. So grid search CV, when I fit it inside grid search CV, it will by itself do cross-validation and select the best parameter. And it will return a model that is fitted with this best parameter. Okay, so if we run it, we see that it selects for ridge a best parameter of 0.06. So here it makes it. And for Lasso, a best parameter of 0.01 here. So I'm going to skip this. Well, the only thing you need to know here is that Rich CV and Lasso CV do the same thing as Grid Search CV, but they're specific to Rich and Lasso. And now I can do a proper cross-validation. So now what I'm doing here is I'm doing a cross-validation on a model that is itself using internal cross-validation to select alpha. So each of these models is not given a single alpha, it's given a list of alpha. And internally, what it will do is it will do cross-validation to select the best alpha, okay? So it means I'm doing cross-validation on models that themselves select the best alpha. And if I do this, well, I don't know why you can't see it here, but if I do this, I will find that actually Lasso doesn't perform as well as Ridge. And the reason is that if we go back to this curve, the peak here is very narrow. And so it's very hard to select the best possible parameter. So if I select the best possible parameter for one data set, and you give me a new data set, I will fall off. And this will cost me a lot. So the Ridge doesn't have this problem. It's much more flat. And selecting the best parameter here was an overfit. I had learned something that does not carry out to new data.